Hello everyone, welcome to online class of Electrical Machines 1 subject. This is Asra Sultana, Assistant Professor in Triple Department. So in the previous classes, we have seen a auto transformer, construction of auto transformer we have seen, its operating principle, applications and comparison with two winding transformer. So auto transformer major advantage is that instead of two windings, we are using only one winding. And by using one winding, what is the use? So only one winding requires less copper. So less copper means it will be cheaper than the two winding transformer. Economical, okay? It is economical. So and limitations also we have seen for auto transformers. So the use of auto transformer is very limited, okay? And construction wise, if we see auto transformers, its construction we have seen it is also of step up and step down type. It will also have N1 N2 number of turns on primary and secondary windings, okay? But a part of the winding will act as a primary winding and a part of it will be acting as a secondary winding. And one important difference between a normal two winding transformer and auto transformer is that in auto transformer, the windings are both electrically and magnetically linked. Whereas in an ordinary transformer, uh, in auto transformer, they are linked both electrically and magnetically. In ordinary two winding transformer, windings are linked only magnetically, but electrically they are separated. Okay. And what is it normal in two winding transformer? What is the operating principle? Mutual induction. So same is the case with auto transformer. What is mutual induction? So there are two windings in a transformer. One is called primary, another is called secondary winding. Primary winding is the one to which we are applying the AC voltage. Secondary winding is the one to which we are giving the load. Okay. So why we are giving AC only to transformer? Does transformer work on DC? No, transformer does not work on DC because what is happening if there is a DC voltage applied, current or voltage will not change with respect to time and EMF will not be induced because there should be a change in flux linking with the coil for the EMF to be induced. But if there is no change in flux, no EMF is induced. So that is why transformer will not work on DC. It will work only on AC. So we are applying alternating voltage to the primary winding, alternating current will be flowing in the primary winding and alternating flux will be created. This flux is changing and whenever flux is changing in the coil, EMF will be induced, that is self-induced EMF. Then the same flux is linking with the second coil also and EMF is induced in the second winding also, that EMF is mutually induced EMF, and whenever a load is applied to the secondary side, current will start flowing through it. Okay, so now we are having voltage, current and number of turns and EMF induced on primary side, voltage, current, EMF induced, number of turns on secondary side. Okay, both on primary and secondary sides we are having. Then we have seen the EMF equation of transformer. E1 is equal to 4.44 F phi m N1. Okay, phi m is equal to Bm into A. So at that time what we have seen, E1 by N1 is equal to E2 by N2 equal to 4.44 F phi m. So this was constant part. We have seen the voltage transformation ratio E2 by E1 is equal to N2 by N1 is equal to I1 by I2 equal to K. That also we have seen. Ideal transformer we have seen. What is an ideal transformer? Ideal transformer is one which has no winding resistance, no leakage flux and no iron losses in the core. So input should be equal to output in the case of an ideal transformer. But in a practical transformer, this will not happen. And we have seen each and every case, that is ideal transformer on no load, practical transformer on no load, ideal transformer on load, practical transformer on load, and phasor diagrams for each of them we have seen it. Okay. If load is connected, resistive, inductive or capacitive, it can be anything. And for that also we have seen separately three diagrams I have shown you. So all of you, please go through all the videos, previous videos. If you have any doubts, you can ask me. Then equivalent circuit we have seen. Equivalent circuit of no load transformer, no load equivalent circuit we have seen. Then equivalent circuit of a transformer. Then equivalent circuit referred to primary and referred to secondary also we have seen. Voltage regulation we have seen. Losses and efficiency. Two types of losses, iron and copper losses are there in a transformer. Okay. Then efficiency we have seen. Efficiency is output power by input power. We have seen the condition for maximum efficiency. Various tests were conducted on transformer. Okay. Open circuit test, short circuit test, polarity test, back to back test. Then separation of hysteresis and eddy current losses we have seen. Three phase transformer construction, types of connections, their comparative features I have said you. Parallel operation of single phase and three phase transformers also we have seen. Auto transformer construction, principal application and comparison with two winding transformer, and about what is the saving of copper, that derivation also I have said you. Okay. So now in today's class I'll be saying you about Scott connection. Scott connection is also called as 3 to 2 phase conversion. Then its phasor diagram, applications of Scott connection. Then I am going to tell about 3 to 1 phase conversion, 3 phase to 6 phase conversion. Okay. So remaining is one more topic will be there. One more class I'll be finishing the subject 5 units, that is tap changing transformers. Under that, no load and on load tap changing transformers and 3 winding transformers. Okay. These two topics, tap changing transformers and 3 winding transformers, in the next class I will be telling you. In today's class, quad connection and 3 phase to 6 phase conversion, which is given in the syllabus, that part will be completed. Okay students, so let us start the class. So Schottky transformer connection or 3 phase to 2 phase conversion. Let us see the definition. Schottky connection is the method of connecting two single phase transformers to perform the 3 phase to 2 phase conversion and vice versa. So vice versa means what? We can convert it to 3 to 2 phase or 2 to 3 phase. So Schottky connection, this connection of 3 to 2 phase conversion is also called as Scott connection. So usually we tell this as Schottky connection, and in this Schottky connection method we are connecting two single phase transformers to perform 3 phase to 2 phase conversion and vice versa. Two transformers will be connected electrically but not magnetically. Okay, so please note down this point. Transformers are connected electrically but not magnetically. One of the transformers is called as main transformer and other transformer is called as auxiliary or teaser transformer. So one transformer is main transformer, other transformer is auxiliary or teaser transformer. So this is the Scott connection of transformers. On the right hand side you can see this is the diagram. So very important question, this will be asked in long questions, LAQ. So you have to draw this diagram also. So this figure is showing the Schottky transformer connection. Main transformer is center tapped at D and it is connected to the line B and C of the three phase side. So main transformer is center tapped at D. This is main transformer. Okay. And it is center tapped at point D and is connected to the line B and C. So this is main transformer is connected between line B and C and it is center tapped at point D. It has primary BC and secondary A1, A2. Okay, primary is BC, secondary is A1, A2. Teaser transformer is connected to the line terminal A and the center tapping D. So this is teaser transformer, this one. So between A and point D, this teaser transformer is connected. It has primary as AD. So this is the primary of teaser transformer AD and secondary is B1, B2. So this is B1, B2. So this is main transformer, this part, and this is teaser transformer. Identical interchangeable transformers are used for Schottky connection, in which each transformer has primary winding of TP turns and it is provided with a tapping at 0.289 TP, 0.5 TP and 0.866 TP. So for a Schottky connection, identical interchangeable transformers are used, in which each transformer will be having a primary winding of TP turns and tappings will be provided at various positions. These are the fixed points. 0.289 TP, 0.5 TP and 0.866 TP. This is the phasor diagram of a Scott connection transformer. So this is the three-phase input voltage VAB, BC, CA. All three are displaced from each other by an angle of 120 degrees. Voltage on transformer primary winding. So this is the voltage this is N neutral point. AB, BC, CA. This is root 3 by 2 VL. This value. This is VBD, VDC. So line voltages of three-phase system VAB, BC and CA which are balanced. That is why they are displaced from each other by 120 degrees, okay, as they are balanced. So same voltage will be shown as a closed equilateral triangle. So the same thing we are showing as a closed equilateral triangle. Figure is showing the primary windings of the main and TZ transformer. So VAB is equal to VBC equal to VCA. That can be taken as VL, line voltage. AB, BC, C are the line voltages and they are represented as VL. So D divides the primary BC of the main transformer into two halves and hence the number of turns in portion BD is equal to number of turns in portion DC, that is TP by 2. Okay. So BD plus DC is giving us BC and each portion is now becoming equal to half of the TP. So TP by 2, TP by 2. Voltage VBD and VDC are equal and they are in phase with VBC. So now VBD is VDC is half VBC, that is half of VL, because we are taking this as line voltage VL. So half VL which is less than 0 degree. So voltage between A and D is now VBD is VDC is 1 by 2 VBC, that is half VL, that is VAD equal to VAB plus VBD. Okay, AB plus BD is VAD. Now substitute the values. This is VL into minus or VL by 2 plus J root 3 by 2 into VL. So I am taking VL as common. So minus 1 by 2 plus J root 3 by 2 plus half VL. So VL if you take, because the entire thing we can take VL as common. So it is becoming now this half and half gets cancelled. So J root 3 by 2 or root 3 by 2 value is 0.866 VL. 0.866 VL is less than 90 degrees. So TZ transformer has primary voltage rating, that is root 3 by 2 or 0.866 of the voltage ratings of the main transformer. Voltage VAD is applied to the primary of the TZ transformer and therefore secondary of the voltage V2T of TZ transformer will lead the secondary terminal voltage V2M of main transformer by 90 degrees. So what we are telling here is that TZ transformer is having primary voltage rating 0.866 of the voltage rating of main transformer and VAD is applied to the primary of the TZ transformer and therefore secondary of voltage V2T of TZ transformer will read the secondary terminal voltage V2M by 90 degrees. Okay, between V2T and V2M angle is 90 degrees. Vs1 by VAD is Ts by TAD or V2T equal to Ts by TAD into VAD, that is Ts by root 3 by 2 TP into root 3 by 2 VT. So we can write this as Ts by TP into VL is V2M. For keeping the voltage per turn same in the primary of the main transformer and the primary of the TZ transformer, number of turns in the primary of the TZ transformer should be equal to root 3 by 2 TP. So secondaries of both transformers should have equal voltage ratings. V2T and V2M are equal in magnitude and 90 degrees apart in time. So they result in a balanced two-phase system. Let us now see the position of neutral point N. Primary of the two transformers may have a four-wire connection to a three-phase supply if the tapping N is provided on the primary of the TZ transformer such that voltage across AN equal to VAN, that is phase voltage V1 by root 3. Since the voltage across portion AD is VAD is root 3 by 2 VL. So voltage across the ND can be written as VND is VAD minus VAN, that is root 3 by 2 VL minus VL by root 3. So it will become VL by 2 root 3. Same voltage turn in portion AN, ND and AD are shown by the equations as TAN, TND. Okay, so TAN equal to TP by root 3, that is 0.577 TP. TND is TP by 2 root 3, 0.288 TP. TND is now equal to root 3 by 2 TP, 0.866 TP, and AN by ND, that is TAN by TND equal to 2. So the equation above shows that neutral point N divides the primary of the TZ transformer in the ratio AN is to ND as 2 is to 1. Let us see now applications of Scott connection. Following are the applications of the Scott-T connection. First one is Scott-T connection is used in electric furnace installation where it is desired to operate two single phase together and draw the balanced load from the three-phase supply. So it is Scott connection applications are in electric furnace installation where it is desired to operate two single phase transformers together and draw the balanced load from the three-phase supply. Second application is that it is used to supply the single phase loads such as electric train which are so scheduled as to keep the load on the three phase system as nearly as possible. It is used in electric trains. Third one is Scott connection is used to link a three phase system with a two phase system with the flow of power in either direction. Scott-T connection permits conversion of a three phase system to a two phase system and vice versa. But since two phase generators are not available, converters from two phases to three phases are not used in practice. Now let us see three phase to one phase conversion. A single phase power pulsates at twice the frequency while the total power drawn by a balanced three phase load is constant. Thus, a single phase load can never be transferred to a three phase system as a balanced load without employing some energy storing device like capacitor, inductor or any rotating machine. So, suitable transformer connections can be used in distributing a single phase load on all the three phases, though not in a balanced fashion. So, we can convert a three phase into single phase. So, single phase power pulsates at twice the frequency while total power drawn by balanced three phase load will be constant. So whatever load which is drawn by a balanced three phase load will be constant, but input voltage is pulsating at twice the frequency. So single phase load can never be transferred to a three phase system because balanced load without employing some energy storing device like capacitor, inductor or rotating machine. So suitable transformer connections are used in distributing a single phase load on all the three phases, though not in a balanced fashion. So for a large single phase loads, this is better than allowing it to load one of the phases of a three phase system. Variety of transformer connections are possible. So there are two figures here. A figure is showing how Scott connected transformer can be used for this purpose and B figure is showing the corresponding phasor diagram. So three phase can be converted into a single phase. These are the circuit diagram and the phasor diagram. Now we will see the three phase to six phase conversion. Each secondary phase is divided into two equal halves with polarity labeling. So six phase voltages, that is 360 degree by 6, that is 60 degrees, are obtained by means of two stars in phase opposition, each star being formed from three respective half windings as it is shown in the figure. So this is a three phase delta connection and this is a six phase star connection. We are converting a three phase delta to six phase star connection. So this connection will be employed in rectifiers and thyristor circuits where a path for the DC current is needed. Thank you everyone for watching the video. So I hope today's class is clear to everyone. Note down all the diagrams, circuit diagrams and phasor diagrams. So Scott connection and three phase to six phase conversion, very important topics, important for internal external both. Thank you everyone for watching the video. And students, give your attendance in comment section.